All right, so chapter 3. So test 2 is all about probability and probability distribution. So we're kind of getting more into the idea of what we'll be doing for the rest of the semester. So probability is going to be our chapter 3, talking all about probabilities. Where chapter 4 is going to talk about probability distributions. Probability distributions. So in doing so, let's kick it off. So an experiment, always we start off with our vocabulary. An experiment is a process that when performed results in one observation or one outcome. So an outcome is a possible observation of an experiment. The sample space is the collection of all the outcomes together, and we label it or we denote it using the letter capital S. Capital S is for our sample space. An event is a collection of one or more of the outcomes of an experiment. We have two types of events, simple event and compound event. A simple event is an event that includes only one final outcome, and it's denoted by E sub I. So notice that sub I is just our labeling. So our first event would be E sub 1, second event would be E sub 2, E sub 3, E sub 4, all that good stuff. So that's just our way of labeling it. A compound event is an event that includes two or more of the final outcome, and it's denoted by the letter A. We'll see some of these here in a minute. Almost done. So probability is numerical measurement of the likelihood that a specific event will occur. We label it by P of X. So this is the probability that X is going to occur. So probability of X occurring. I had a lot of you for algebra. It's the same as function notation. So for example, if you want the probability that you're going to land on heads, it would say P and then in parentheses head, like probability of landing on heads. This is our way of labeling it and kind of telling us what's the probability and what's the probability that we're looking for. So we have two properties for probability. Our first property is the property that the probability of an event always lies between 0 and 1. 0 means it's definitely not going to happen. 1 is like it's for sure 100% going to happen, and then everything in between. So we label that as 0 is less than or equal our probability of an event. So E sub I is less than or equal to 1. Our probability of an event happening is between 0 and 1. Notice that 0 is included, so our probability could be 0. If I flipped a coin, what's the probability I'm going to land on a 2? There's no 2 on a coin, so it's not going to happen, so it's going to be 0. All the way to 1, where 1 is 100% going to happen. If I have a bag of marbles and there's only red marbles, what's the probability I'm going to reach in and grab a red marble? 100%, because it's only going to be red. Our second property is the sum of the probabilities is always an equal 1. If you add up all the probabilities together, that gives you everything. Everything means 100%, which would mean 1. So writing this algebra or statistically, we have our sigma, which remember means the sum of, our probabilities of our events, which would mean the probability of 1, E sub 1, plus the probability of E sub 2, plus the probability of E sub 3, plus so on and so forth, is going to always add up to equal 1. Right. Yes, so I'm glad that you said that. So yeah, so in between 0 and 1, usually our probabilities are in decimal form. You can also put it in percent form. So 0 would be 0%, 1 would be 100%. And it'll tell you on the homework how to label your, it'll say like, does it want a percent or does it want a decimal? But most of the time here we use decimals. But it would represent 100%. You're right, 1 represent 100%. Great question, thank you. What else? All right, so looking at these two properties, this first example just says, which of the following values cannot be a probability? And select all that apply. Remember our two properties. The number has to be between 0 and 1, and then you have to add it up to give us 1. Is 1.2 between 0 and 1? No, it's bigger. So which ones cannot? So that's one we're going to circle. 0.97. I'm going to write a little note here, by the way. I'm going to say over 1, just so that way you know whenever you go home why we chose that one. 0.97, that's fine, in between 0 and 1. 1.0, that's fine. 1's included. It could be 1. 1/4 is the same thing as 0.25. That's in between 1, so it's okay. Negative 1/2. No, I can't have a negative. So negative 1/2 is not an option. I don't like that there. Eight over 7. Bigger than 1, so no. Negative 0.30. Nope, can't be negative. And 0. Yeah, it's fine. It's okay that it's that 0 because 0 is included in our answer. So anything that's less than 0 or greater than 1 doesn't work. I love that problem. I wish the whole test was like that, then we're done. All right, stop me if you have a question. If not, I'm going to keep rolling. So the next example, choose the correct sample space, which is S, for the random experiment that is described. Remember, S up here is the collection of all outcomes, so all are possible outcomes. So what are the possible outcomes if a pair of dice is rolled and the sum of the dots on the two faces that come up is recorded? So before I do that, let me just put a little note. Can be any number between 0 and 1, including 0 and 1. I said it, but I didn't write it for probabilities. Can be any number between 0 and 1, including 0 and 1. So going back to our example about a pair of rolling dice. So what are these options? If I were to roll two pair of dice, our dice, remember, have different sides from 1 to 6. What are our different outcomes? Looking at my first one, my first option is 1. Well, if I roll 2 die, the smallest number on both of them was going to be 1. If I add up, that would give me 2. So I could never just get 1. So this is not an option. I can't have 1. That means, by the way, this last one's not an option. So if I have, again, a pair of dice, so 2 die, I roll them, and then I add up the numbers of dots that are on their faces. All right, so 2 is an option. So we're looking at, like, what is this, B and C? 3, could I get 3? Yeah, I could have 2 on one die and 1 on the other. 1 and 3. 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is good because if I have 6, which is the maximum on both of them, will give me 12. Here, what's missing? I don't have 3, but 3 is an option. So this doesn't give me all of my options. So my answer would be, I guess you could say B. This gives me all possible outcomes. All possible outcomes. Please stop me if you have a question. If not, I'm just going to keep rolling. So 3 approaches to probability. We have classical probability is our first approach. Classical probability means that all simple events are equally likely. All simple events are equally likely. So to find classical probability, the classical probability rule for a simple event just means that 1 out of the total number of outcomes, or for a compound event, that means the total favorable outcomes over the total number of outcomes. This is like our typical probability that we always see. We're going to see an example next, but let's look at the next type. So that's classical or normal probability. On the next page is what's called relative frequency. Talking about our relative frequency from test 1. our probability of A occurring is going to be F, which is our frequency. So frequency that event A occurs, all over N, which is the number of times the experiment is done, or performed, I guess. The number of times the experiment is performed. And it says that here. So N is the number of times the experiment is repeated. F is the frequency the event A occurs. It's also called empirical probability. So empirical probability is important. Another word for empirical is experimental. So whenever you see the word empirical, it means experimental. We're actually performing an experiment. We're actually taking the data in and testing it to see what our data, what our numbers really are. So it's kind of like classical probability is just in theory, right? So in theory, so if I were to flip a coin, in theory, I should get 1 out of 2 for heads, my probability of heads, 1 out of 2, my probability for tails. Relative frequency means, okay, what if I actually flip the coin 10 times? How many times does the coin actually land on heads in my experiment? Whereas subjective probability is our last probability, and it's a probability assigned to an event based on subjective judgment, beliefs, or hunches. So we're going to see an example of this next. So the next example says which type of probability was used in the following examples, and then find the probability. So classical, relative, or subjective. So it says, the first example, a coin was flipped 31 times and tails was observed 11 times. So they actually performed the experiment. So any ideas? Close. They actually performed the experiment. So relative. So the first one is they actually performed the experiment. So this would be our relative frequency. They actually performed an experiment. They actually flipped the coin 31 times and found that it landed 11 times on heads. So now let's find the probability. So we're trying to find the probability that it lands on tails. So probability that it lands on tails. It told me it landed on tails 11 times, so 11 times is my frequency out of 31 times total. So 31 is my N. In my calculator, 11 divided by 31 would give me 0.354, so that will round to 0.3.
Can you also put empirical, or what you always call it relative?
I believe on this problem it's a drop-down bar, but it's the same thing. So if you put empirical, if you put experimental, if you put relative, they all mean the same. They're all synonyms. So either one would be right. But I think it's on the test, it's gonna be multiple choice, and I think on the homework I can't remember if it's multiple choice or a drop-down menu. Thank you for asking. Anything else? The next example says the probability of drawing an ace out of a standard deck of cards. So this is saying, like, in theory, you're not actually going to pull an ace out, but in theory, what would your probability be? So that's going to be our classical probability. Our classical probability is what's going to happen in theory. So you're not actually performing the experiment. You're saying what should happen. the probability of landing on it or pulling out an ace. So how many aces are in a standard deck of cards?
4.
4. So 4 aces out of how many cards total?
52.
52. You know, I didn't know that until I started teaching statistics. Don't judge. So in my calculator, 4 divided by 52 would give me 0.076. So that will round up to 0.08. 0.08. So we talked about relative, we talked about classical. So the last one's probably going to be subjective, but let's look at it. So there's a 30% chance that I'm going to skip class tomorrow because I'm really tired. I'm really tired every day, but here we are. So this is like no like math, right? I mean, they're just saying 30% chance, but like that's just like from a hunch, or that's just from what we think. So because of that, that's what's going to be called subjective. Probability. Subjective probability. I wrote that like really fast. So based on hunch. All right, so it told me the probability of skipping class was going to be 30%. So it gave us that percentage. Turning that percentage into a decimal, we can take the decimal, which is at the end, and move it 2 places to the left. That would give me 0.30. So those are our 3 different types of probabilities. Those are our 3 different types of probabilities. By the way, just to kind of mention, Ryan, I see, but just to kind of mention on your formula sheet, which is on the back of the notes packet, it has classical probability and relative probability, and it tells you the formulas for those. So just letting you know. Ryan, did you have a question? Yes. So subjective is the only one that would be for, yeah, like I would say like qualitative data. There's still a number to it, but because it's 30%, but there's no like math to it, I guess. Kind of, yeah. So that's a good way to put it. Right. The other 2 are quantitative, yeah, because they are. I mean, this is quantitative too because it's a number, but it's more of, I get what you're saying. It's more of mathy. There's a math to it. We can put a formula to it. Yeah, that's a great way to put it. What else? All right, the next example says use a spinner below to calculate the following probabilities rounded to decimal places if needed. So it gives us this spinner and it asks us to find the probability of landing on 11 or 2. All right, so 11 or 2. So I have 1, 2, and I have 1, 11. So how many favorable outcomes are there? 2. I have 2 things that I'm looking for. By the way, that word or means to add. So there's 1, 11 plus there's 1, 2. So that'll give us 2 favorable outcomes out of how many outcomes total? 12. Perfect. So 2 out of 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 different options. So 2 out of 12 in my calculator would give me 0.16666 all the way to 7. So rounding 2 decimal places, so I'm going to round that second number after the decimal. I'm going to round that 6. Looking next door is another 6, so it's going to round up to 0.17. That's it. Next example, what's the probability of odd numbers attained? So I have 1, 3, 5, 7, 9, and 11. These are all of my odd options. So that means I have 1, 2, 3, 4, 5, 6 options that I'm looking at. Out of, we said 12 total. So in my calculator or in my head, 6 out of 12 would give us 0.5. Last but not least, a multiple of 4. So multiples of 4 would give me like 4, 8, 12. Those are all multiples of 4. 4 times 1 is 4. 4 times 2 is 8. 4 multiplied by 3 is 12. So how I get my multiples. So there's 3 multiples out of 12 total. 12 options total. And give me 0.25. 0.25. So these are all examples of blank probability. Any ideas? Close. We didn't actually spin it, so just in theory. Classical, good. Classical. We actually looked at a formula, so we know it's either going to be relative or classical. We didn't actually spin the spinner, though. If we actually spun the spinner and did an experiment, that would be relative. This is just saying in theory, so it's going to be classical. Awesome. So I'm going to keep going. Stop me if you have any questions. You guys are good at stopping me if you have questions, so I'm not too worried. But the next thing is the law of large numbers. And it says if an experiment is repeated over and over and over again, approaching an infinite number of times, the probability of an event from the relative frequency approaches the actual theory. So what this is saying is if you do it over and over again, kind of like practice makes perfect. If you do it over and over and over and over and over again, the more that you do it, the more that the experiment is going to approach the what's in theory. For example, if I flip a coin 5 times, I might only land on heads 2 times. So that's not going to be that 50-50 I'm looking for. But if I flip the coin 200,000 times, I'd be really close to that 50-50 shot. Not that I want to flip a coin that many times, but I'd be getting more used to it. So it's kind of like practice makes perfect. The more you do it, the more that the relative frequency from the experiment answer is going to get you close to the classical in theory answer. So the union of events, A or B. So you know in math that we like to use symbols because we're very efficient. So instead of writing the word or every time, we use this union symbol. It's like a big capital U. Those of you in college algebra, we used it to unite interval notation together. We said it could be in this interval or in this interval. So it's like a big capital U, and it's the collection of all outcomes that belong to either A or B. A or B. So for example, if I like visuals, so to kind of use a visual, if we have, this is for A, and we have this for B. A or B, it means it could be in A, it could be in both, or it could just be in B. It's everything put together. So our example says, let A be 1, 2, 3, 4, 5, and let B be 4, 5, 6, 7, 8. Determine A or B. So A or B. Notice that we have curly brackets around it. Curly brackets just means it's set. Like that's our answer. There's nothing more, nothing less. It kind of like is parentheses and groups our answer together. So let's keep it in our nice little curly brackets. Don't judge my brackets. So 1 is an option, 2 is an option, 3 is an option, 4, 5, because those are all in A, or it could be in B. So 4, I already have 4, so I don't need to write it again. It's already understood that these are all my different options. 4 is already there. Just like a Venn diagram, I wouldn't write it twice. It would be in this middle part because 4 is in both of them, so I don't need to write it twice. Same thing for 5, but 6 is an option, 7, and 8. So basically, we're going to put them all together, but don't write the duplicates. So putting it all together, don't write the duplicates. A or B. So the word or means it could be in A, it could be in both, or it could be in B. Those are all of our options. Same thing for the intersection. The intersection is for, just like the Venn diagram, where it intersects. So where it intersects is what they have in common. So for our intersection, instead of like our U symbol for the unite, this is like an upside down U. I know it's kind of weird, but I think about it as an N. It kind of looks like an N, kind of like the N in and. So A and B is a collection of objects that are in common to both A and B. So if we were to draw our little Venn diagram again, here's everything that's in A, here's everything that's in B. A and B is what they have in common, the intersection where these two circles intersect. So if we have A being 1, 2, 3, 4, 5, and B being 4, 5, 6, 7, 8, determine A and B. So A and B. So what does A and B have in common? 4 and 5. So just 4 and 5. And that's it for that page. Questions before I go on to the next page? So next, is joint probability, which is the probability of going to that A and B. So we talked about the intersection of A and B. Now joint probability is finding the probability of those two. The probability of the intersection of two events. It looks a little blurry to me. Let me try to fix it for you. It's a little better. The complement of an event is the collection of all possible experimental outcomes that are not in the set, that are not in A. We denote it or we label it as, we call it A naught. So it could be A with like an apostrophe, it could be A with the hat on top, with the line up top, or I even seen it as A with a little C as an exponent. So let's do an example of this. So it's whatever that's not in A. So if our sample space, if every option is 1, 2, 3, 4, 5, 6, A is 1, 2, 3, 4, determine the complement of A, then find the probability of A and the probability of the complement. So if we know A is 1, 2, 3, 4, the complement of A so 1's in A, 2, 3, 4. So 5 and 6 are not in A. So the complement is going to be 5 and 6. What's in the sample space that's not in A? So 5 and 6. We found the complement. Then find the probability of A. So the probability of A. We have 1, 2, 3, 4 options out of 1, 2, 3, 4, 5, 6 options total. So my calculator, 4 divided by 6, I know my battery's low, would give us 0.666, so we can round this up to 0.67. And the probability of the complement of A, I have 2 options out of my 6 total. So 2 out of 6 would give me 0.333, which is 0.33. One little note, because we're going to use this in a minute. If we have the probability of A plus the probability of the complement, any ideas on what that would give us? So A gives us everything that's in A. A naught, the complement of A gives us everything that's left over. So putting that together would give us everything. How do I show my probability as showing it as everything? 1, bingo. So my probability would be 1 if I add those together. It would give me everything in the sample space. It would give me, adding the probabilities together would give me 1. So sometimes, for example, if they give you the probability of A, but we don't know the probability of the complement of A, we can use this and use algebra to kind of solve for different probabilities. We'll get to that in the future though. Next is marginal probability, which is the probability of a single event without the consideration of any other event. So we don't think about anything else, we just worry about that single thing. It's also called simple probability, where the opposite is what's called conditional probability. It's the probability that an event will occur given that another event has already actually occurred. So we are actually considering something else. We denote it as the probability of A given B. So that vertical bar means probability of A given B has already occurred. For conditional probability, we can use Bayes' theorem. Bayes' theorem is on your formula sheet. The probability of A given B, which is the probability of A and B that we already talked about previously, joint probability, all over the probability of B. Notice that it's given B, so B is kind of like in my denominator here. Like it's not a fraction, but to me it kind of looks like a fraction. So it's kind of like in the denominator, so it kind of goes in the denominator here. So that kind of like helps me remember. It's on your formula sheet too, but it kind of helps me remember. The reason why is because B already happened. So we are only considering things given that B already happened. If we see an actual example, sometimes it's easier. So let's do it. So the probability that a randomly selected IRSC student is an athlete is 0.16. I'm going to go ahead and write that out. So probability that the student is an athlete is 0.16. The probability that a randomly selected IRSC student is a biology major is 0.14. So probability that they are a biology major is 0.14. And the probability that a randomly selected IRSC student is a biology major and an athlete, so both, so probability of biology and an athlete, remember that word and is like our upside down U, is 0.13. I just like to be super organized, so instead of reading through that whole paragraph, I like to say, okay, this is what the paragraph gives me. And that way I don't have to go rummaging through it. I know exactly what information is given. The question asks us to calculate the following probabilities, round to 3 decimal places if needed. So determine the probability that a randomly selected IRSC student is a biology major given that the student is an athlete. So probability, that word given is important. Probability that it's a biology major given, so given's our vertical bar, that the student is an athlete. So given athlete. So what that's saying, if you were to think about it in a more tangible sense or more real world scenario, what that's saying, instead of just looking at all biology majors, it's saying, okay, let's put all the athletes in one room. So now just looking at those athletes, just looking at those people who are athletes, now out of this smaller group, how many are biology majors? So it's not considering anyone else, it's only considering athletes. So they give us everything that we need. Let's plug it into our Bayes' theorem up here. So our Bayes' theorem says probability of the first thing, which in this case is A, so biology, and the second thing, which is athlete, over the probability of the second thing, which the second thing is an athlete, so using this Bayes' theorem, A and B are just generic. In this case, our first thing, our A is biology, and our B is our athlete. My point here is the order really matters. So the first thing is probability of biology and athlete, all over the probability of athlete. Remember how it looks like athletes kind of like in the denominator and then athletes in the denominator here. So probability of biology and athlete, which is 0.13, all over probability of just an athlete, which is 0.16. Plugging that into my calculator. 0.13 divided by 0.16. Rounding it set at 3 decimal places, we would get 0.8125, which would round up to 0.813. Same thing for the next one, I just swapped the order. So determine the probability that a randomly selected IRSC student is an athlete, given the student is a biology major. So this time it's going to be the probability of an athlete given biology. Putting this into our Bayes theorem. Probability of athlete and biology divided by the probability of biology if they're an athlete and they're a biology major, it doesn't matter if you say athlete and biology or biology and athlete. Either way, they're both. They're both an athlete and biology major. So it's going to be the same probability, so 0.13 divided by probability of biology major, which is 0.14. So my calculator is 0.13 divided by 0.14, which would give me 0.9285. We'll round up to 0.929. So moral of the story is the order does matter, so be very careful.
Do you always want us to round 3 decimal places?
No, the question specifically said 3.
Oh.
It'll tell you in the homework. And then on the test, it's multiple choice. Thank you for asking. What else? What other questions? All right, so the next thing independent events are 2 events that are independent if the occurrence of one does not affect or does not change the probability of the occurrence of another. And to prove that, we're going to use this conditional probabilities. We're going to say that a probability of A given B has to be the same thing as probability of A in order for them to be independent. For dependent events, 2 events are dependent if the occurrence of one does not change or affect the probability of the occurrence of another. So if they're not equal, the probability of A given B is not equal, that means they are dependent. We'll see that in a minute. A couple more definitions. Sampling with replacement is exactly what it sounds like. A unit is selected at random from the population and it's replaced. So it's sampled out and then it's returned to the population before another unit is selected. And then sampling without replacement is a unit selected at random from the population and it's not returned. So with replacement means that you put it back before selecting another one. Without means that you take it out and you leave it out. No, always assume that 2 events are dependent unless we can prove otherwise. So in general, they're usually dependent unless we can prove otherwise, which we're going to prove on the next page. Questions on this page before we go to the next page? All right, so on the next page. For this one, I wish there was an easier way. We're gonna do it. Okay. It says an experiment consists of randomly selecting a single digit, so from 0 to 9, where each digit is equally likely to be selected. Define the following events. So A, B, C, and D. So A is an even digit is selected. So our options for even are going to be 0, 2, 4, 6, and 8. So from 0 to 9, we have 0, 2, 4, 6, 8. For B, a digit greater than 3 is selected. So something more than 3. So 4, 5, 6, 7, 8, or 9. C is a digit less than 7. So 0, 1, 2, 3, 4, 5, or 6. And then D is 1 or 7. So just 1 or 7. By the way, it told us that 0 is an even number. Sometimes there's controversy about that, but it told us to use 0 as an even number. 0 is just 0. All right, so it asks us which two events are dependent. So, I'm sorry, which two events are independent? So remember, going back to prove independency, I don't know if that's a word, independency, I don't know. To prove that they're independent, here's what we have to do. Probability of A given B equals the probability of A. And by the way, just to show you, that it's on your formula sheet right here. Probability of A has to be the same thing as probability of A given B, or the other way around. So let's do it. So for B and C, that means the probability of B given C has to equal the probability of B. Probability of B given C has to equal the probability of B. So in order to find the probability of B given C, you can do what we just did. But now that we have actual numbers here, there's kind of an easier way of just kind of thinking about what would happen. So probability of B given C, that means we're only looking at C. Our only options are 0, 1, 2, 3, 4, 5, 6. That's our only options. So that means I have 1, 2, 3, 4, 5, 6, 7 options. So out of these options, how many options from B, it's like probability of B and C, how many do they have in common? They have 4 in common, they have 5 in common, and they have 6 in common. So that means they have 3 numbers in common, so B and C. Out of 7 options total. So 3 7ths. So in my calculator, 3 divided by 7 will give me 0.429. 0.429. And we're trying to see, is this the same thing as the probability of B? So B means we have 1, 2, 3, 4, 5, 6 options in B. Out of, we said we had from 0 to 9. So if we count 0, that will give us 10 options total. So 10 options total. So in my calculator, 6 out of 10 would give us 0.6. So that means they are not equal. So that means they are dependent. They are not independent. Didn't work. We're going to do the same concept for A and D. So probability of A given D has to equal the probability of A. So if we're looking at our options for D, in D we have two options, 1 and 7. Out of how many are in common for A and D? 0. So 0 divided by 2 is just 0. And does that equal, is that the same thing as just A? Well, A has 1, 2, 3, 4, 5 options in A out of 10 total. So 5 out of 10 would give us 0.5. So 0 does not equal 0.5. So A and D are dependent. They are not independent. Last one, A and B. Let's go up here, I guess. So probability of A given B has to equal the probability of A. So probability of A given B. So starting at the bottom. So we're just looking at what are our options for B. I have 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6 options. Out of those 6 options, how many, just looking at 4, 5, 6, 7, 8, 9, how many does A have in common? They both have 4. They both have 6. They both have 8. So that gives us 3 options in A and B. Out of 6 options total, 3 out of 6 would give us 0.5. And then what's the probability of A? So A have 1, 2, 3, 4, 5 options. Out of, we said we had 10 options total. This is why we put it into decimal form, because 5 out of 10 is 0.5. So even though they look like different decimals, they're still both 1/2. They're still both 0.5. So that worked. So because A and B worked, A and B are independent, and that would be our answer. So if you have a question, I'm going to keep rolling so we can get through everything. So the next example says, in a class of 32 students, 12 are dual enrollment and 20 are not dual enrollment. Suppose 2 students are randomly selected from the class without replacement. So that's important, without replacement. Calculate the following probabilities around to 3 decimal places as needed. So what's the probability that both students are dual enrollment? Okay, so to do this, we're going to find the probability that the first student is dual enrollment. So how many dual enrollment students are there? 12. So 12 dual enrollment out of how many total? 32. So 12 dual enrollment, so this would be D, dual enrollment, out of 32 total. And then we're going to multiply this by the second option. So remember, that student is taken out of the class and not put back. So if that one student is taken out and not put back, how many dual enrollment students are left over? 11. So dual enrollment left over. Out of how many students are left over total sitting in the class? Remember that one student was taken out. The first student was taken out and he didn't come back in, or she. So 31. Total left over. So that without replacement is important because that means they went out of the classroom and they didn't come back in, so they weren't an option. So that's what changed our numbers for the next one. So now if we have 12 out of 32 times 11 out of 31, plugging that to my calculator, When you do so, make sure to put it in parentheses. So in parentheses, 12 divided by 32, 2. So that's saying, okay, that's my first fraction, times my second fraction, which is 11 out of 31. If you don't put in parentheses, it'll take the fractions and make complex fractions, which is not what we want. And rounding at 3 decimal places, we have 0.133. That's it.
Why didn't we take 2 students out?
We did. This is the first student. So we took that student out first, and then we took out the second student. We like didn't take them both out at the same time. Like you have to take one student out and then take another student out.
No, it's not looking. Where did you take the first one out?
Right here in blue. So the first student, there's out of like, say this was the class, right? So out of this class, there's 12 people in here that are dual enrollment. Let's say Savannah, I'm going to call you out, sorry. Savannah is the first student that was chosen. So she was out and she goes out the door and doesn't come back in, right? So she was already chosen. And there was 12 dual enrollment out of 32 total. Now that she's out, that means 11 students are left over. So that's like what's in green to choose from. And then now there's only 31 people because she's outside. So think of the first student first, and then we chose the next one. Let's look at the second example. That might help you too, because it's the same concept. So the second one says, what's the, so we, like just wrapping that up. We did take out 2 students. Here's my first student that we took out. Here was Savannah, and then here was the second student, whoever that is, that came out. If we did the third, there'd be another fraction in there too. Or if we did 4, there'd be 4 fractions. So the next example says, what's the probability the first student is dual enrollment? So taking that dual enrollment student out, and the second student is not dual enrollment. Okay, so same concept. So let's look at our first student. They are dual enrollment. So how many dual enrollments are there? 12 out of 32 total. So that's our first student. So times our second is not dual enrollment. So how many non-dual enrollments are there? 20. So 20 not DE. Okay, we took out 1 student. So how many students are left over to choose from? 31 again. So total left over. Same concept, putting this into our calculator. It's 2 separate fractions, so make sure to put your parentheses. In parentheses, 12 divided by 32 times in parentheses 20 divided by 31. And we get 0.2419, which will round up to 0.242. Fair warning, in the homework, you know how there's videos for every problem? They do it differently, and I think the way they do it is way harder. So I'm not even going to like open that can of worms, so I don't want to confuse you. But if you want a different option, there's a different option there. They use the conditional formulas and plug it into a formula. From my experience teaching this class, I used to teach it that way, but I feel like this way is a lot easier than I taught both, and I don't want to confuse you. I feel like this way is the easiest, in my opinion. So this is, just want to throw that out there. If you see a different way on the video, that's why. But however you get the answer is fine. I don't care how you get it, just get the answer. Questions on this one before we go to the next one? There's another problem in the homework that's about like wearing eyeglasses or something that's just like this one. So this one will be in there and another one that's similar. So the next example says a random sample of 175 students were asked what kind of vehicle they preferred, a car or a truck. The following contingency table, which is just like this, what is it called in biology? Like a Punnett square. Same thing. It's just a way of organizing our data. Gives a 2-way classification of the response. So their answers are either car or truck, and then they're asked are they male or female. So 89 males said they liked cars, 26 males said they liked trucks, 50 females said they liked cars, and 10 females said they like trucks. So we're looking at two-way classification. So we're looking at two separate answers, whether they answered car, truck, and whether they answered male or female. For these, I like to, just like we talked about earlier, have all of my information up front at once, so that way I'm not doing the math behind the scenes. I'm just looking at it and here's my answer. So based off of this table, let's find some totals. So total, going across, how many males were asked? Well, 89 of them said cars, plus 26 said trucks. So total, I have 115 males that were surveyed. Same thing for females. If we have 50 that said car and 10 that said truck, that means we have 60 females total, which makes sense because 115 plus 60 would give me that 175 that they told me in the problem. So it's kind of like a way of checking your work. 175 people total. Same things for car versus truck. So how many people said car in general? I don't care male or female. So 89 males plus 50 females together would give me 139 people said car. And 26 plus 10 would give me 36 people said truck. So 36 people in general, I don't care male or female, said truck. Adding that up just to check our work, 139 plus 36 should give me my total of everyone, which is 175, which it does. So here's everything that I need on my chart. So it says, suppose one student is randomly selected from the group, calculate the following probabilities, rounded 3 decimal places as needed. So what's the probability of female? So now we kind of found it. So females, we know our total females are 60. Out of how many people total? 175. So 60 out of 175. Notice I don't care car or truck, female in general. And this would give me 0.3428, which will round up to 0.343. Next we have car. So how many people said car? I don't care if male or female.
139.
Good, 139 said car. Out of that 175 total. So 139 divided by 175 would give us 0.7942, which would round to 0.794. So these are what's called marginal probabilities. Remember, marginal probabilities is the probability when I don't consider anything else. I didn't consider car or truck for this first one. I didn't consider male or female. I just thought probability of female, just thought probability of car. So these are marginal probabilities. Marginal. Where the next two, notice that vertical bar, that means given. So these are going to be conditional probabilities. These are going to be conditional probabilities. So probability of female given truck. All right, probability of female given truck. So looking at our chart, the chart really helps us here, makes this so much easier. How many people, how many females answered truck, or vice versa? How many female truck answers are there? 10, good. Female truck would give us 10. So female and truck. Remember, we're only looking out of our truck. So how many truck options were there total? 36, good. So out of 36, we're only looking at trucks. It's given trucks. So 10 out of 36, which would give us 0.2777, so 0.27, I put extra 7 in. 0.278. So remember, it's kind of like the bottom of your fraction here is the bottom of your fraction here. Same thing, but opposite. Probability of truck given female. So up top, how many females enter truck? Same thing. Still 10. So female and truck. Doesn't matter what order. If you want to say truck and female, that's fine too. Given female. So the bottom is only female. So how many females did we have total? 60. So then we have 10 out of 60, which would give us 0.1666, so 0.17. Zero 0.167. All right, so the last example here says, are the events female and truck independent or dependent? Remember, we had that formula for independence. We said, okay, if it's independent, then the probability of female given truck is going to equal the same thing as just the probability of female. Thankfully, we already found all these for us. That was our condition. That was our way to prove it that we just did on the previous problem. So female given truck, we said was 0.278. And does that equal probability of female, which we said was 0.343? No, doesn't equal. So they're dependent. So dependent. All right, let's take a quick break there. That's kind of a good stopping point. We're about halfway through. Before we take a quick little break, questions, comments, concerns? All right. This quick little break. Let me pause. All right, guys, let's go ahead and get back started and we can wrap this thing up. So next is talking about page 5 is mutually exclusive events that cannot occur together. So ask yourself if the events can happen at the same time. So for example, if you get an A in the class and you get a B, you can't do both. You either get an A or B. You can't happen at the same time. So that would be mutually exclusive. So cannot occur together, cannot occur at the same time. Cannot happen at the same time. We're mutually not, I think about like relationships when you say like you're exclusive, you know, like that's like just you two. And then so mutually non-exclusive means events that can occur together. So ask yourself if they can happen at the same time. So for example, you get an A in the class and you pass. Okay, if you get an A, that means you pass. So that could be, you can do both. So no, assume that two or more, always assume that two or more events are mutually non-exclusive unless you can show otherwise. So let's do an example. There's 164 physicians practicing in Port St. Lucie. Of them, 82 are female and 50 are dermatologists total. Of the 82 female physicians, 10 are dermatologists. So suppose one physician from Port St. Lucie is randomly selected. Answer the following questions. Round to 3 places. So probability of female. So how many females are there total? 82. Out of how many physicians total? 164. Perfect. So 164 total. So in our calculator, it says round to 3 decimal places. 82 out of 164 will give us 0.5. Next, it says probability of female given dermatologist. So remember up top, female given dermatologist. So at the top, this would be female and dermatologist. So 10. So of the 82 female, 10 are dermatologists. So 10 are female dermatologists. Remember, the bottom is dermatologists. So how many dermatologists are there total? 50. Perfect. So 50 dermatologists. So in our calculator, 10 divided by 50 would leave us with 0.2. 0.2. So are the events female and dermatologist independent or dependent? Remember we had that formula. We said probability of female given dermatologist has to equal the probability of just female in order to be independent. We already found these, thankfully. So probability of female given dermatologist is 0.2. And is that the same thing as probability of female, which is 0.5? Not the same thing, so that means dependent. Not equal, so dependent. Last, it says, are the events female and dermatologists mutually exclusive or mutually non-exclusive? So could there be a female dermatologist? Yeah. So there means there are can happen at the same time. Perfect. Can't happen at the same time. So that means exactly right. Mutually non-exclusive. Mutually non-exclusive. Someone could be a female and a dermatologist at the same time. So it can happen at the same time, so mutually non-exclusive. All right, so we're going to take this and add on to it. Questions before we go to the next one? So two basic rules of probability. We have the multiplication rule and we have the addition rule. So for the multiplication rule, that's for and probabilities. If it's the probability of A and B, remember and is like our upside down U. We're going to have the probability of A times the probability of B given A. If they're known to be independent, we can kind of shortcut this, because if they are independent, that means the probability of B given A is going to be the same thing as just the probability of B. So we can kind of shortcut it and just go straight there. So notice for and, you're going to multiply. And then probability rule for addition. If we have the word or, addition rule for or probabilities, A or B. Our ors are union symbol, so like the U. It's going to be the probability of A plus the probability of B, whatever they have in A plus whatever they have in B. You already added what they have in common once, so you can't add it twice. That means you have to subtract the probability of A and B. If they are known to be mutually exclusive, that means they cannot happen at the same time, so they'd have nothing in common. So if they're mutually exclusive, that means the probability of A and B would be 0. They can't happen at the same time. So we can kind of shortcut it, and we don't need this last piece. The probability of A or B would just be the probability of A plus the probability of B. So those are formulas. They are on your formula sheet. Let me just show you real quick. Multiplication rule and our addition rules. So let's do an example. Let AA be the event that a randomly selected IRSC student is an Associate of Arts student, and the probability of AA be 0.34. So I'm just going to write that out so that way I don't have to go up there. Probability of AA equals 0.34. Let the event PM be the event that a randomly selected IRSC student is on the pre-med track. So the probability of PM, probability the student's going to be a pre-med major, is 0.31. Finally, the probability that a randomly selected IRSC student is an AA degree seeker and on the pre-med track, so probability of AA and pre-med is going to be 0.15. Use the information to calculate the following probability, round to 3 decimal places as needed. So what is the probability that a randomly selected IRSC student is AA degree seeker, or remember ors are union symbol, on the pre-med track? So probability of AA or pre-med. So that means we're going to use our or formula. I'm going to be honest with you. I always just use this first one, and then I say that we don't have to worry about, are they mutually exclusive or are they mutually not exclusive. I always use this first one. If they're mutually exclusive, that just means this last thing is 0. So that way I don't have to think about which one is which. So let's write out that formula. So probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B. So we're going to use this formula and apply it to this problem. So wherever I see A in my formula, I'll put AA track. Wherever I see a B, I'm going to put the pre-med track. So our formula should be the probability of AA plus the probability of pre-med minus the probability of both AA and pre-med. We have everything that we need, just plug it in our numbers. Probability of AA we said was 0.34 plus the probability of pre-med 0.31 minus probability of AA and pre-med, which is 0.15. Plugging this into my calculator, 0.34 plus 0.31 minus 0.15 will give us 0.5. Done. 0.5. We're going to do the same concept next before I go to the next page. Questions on this one? One more that's kind of similar to this next. I like this one because it's kind of straightforward. It says use the given information to determine the probabilities below. Round our solutions to 3 decimal places if needed. So probability of A is 0.05. Probability of Z is 0. Probability of B is 0.18. Probability of B given A is 0.11. So if A and B are assumed to be dependent events, find the probability of A and B. So going to our formula sheet, probability of A and B for dependent events. A and B for dependent. Here's our formula. Probability of A times the probability of B given A. There's our formula. From our formula sheet that you have on the test. So it's going to be probability of A times the probability of B given A, which we already have these numbers. So just plugging in, probability of A is 0.05 times probability of B given A is 0.11. So in my calculator, 0.05 times 0.11 will give us our answer of 0.00, rounding 3 decimal places, 55, or we'll round up to 0.006. Done. Next, if A and B are assumed to be independent, find probability of A and B. So going back to our formula sheet, A and B for independent events. So just probability of A times just the probability of B. So probability of A times the probability of B. So A we know is 0.05 times B we know is 0.18. 0.05 times 0.18, and we get 0.009, no rounding. Next is our ORs. So if A and B are assumed to be dependent and mutually non-exclusive, we're going to find the probability of A or B. So going back to our formula sheet, A or B, here are the two formulas, mutually non-exclusive. So we're going to use this first one, probability of A plus the probability of B minus the probability of A and B. Probability of A plus probability of B minus the probability of A and B. So probability of A, they told us is 0.05, plus probability of B, they told us was 0.18, minus the probability of A and B. We found A and B. There's two of them. It told us dependent, so we're going to use this first one. So minus 0.006. Actually, on because I do every problem, it didn't want you to round this. Remember how for this one we got 0. And I have it right here still, 0.0055, and we rounded it. That means we rounded our answer, and then we're going to round it again here. So don't round it. So leave it as 0.0055. And that's always a good rule of thumb. So don't round until your final answer, because if you round and then put it in a problem, you're going to round it again, and then it's going to give you too much off. There's a little bit of wiggle room in the homework, and on the test, there's not going to be different options, but on the tests or on the homework, there's a little bit of wiggle room, but this is the most accurate. So do not round until you get your answers. So until the end to get your answer. (0.05 plus 0.18 minus 0.0055. And we would get 0.2245. Now we're going to round through decimal places, so our answer would be 0.225. Last one. If A and B are assumed to be dependent and mutually exclusive. So A or B, mutually exclusive. So that just means probability of A plus probability of B. So A, we said, was 0.05 plus B was 0.18. Adding those together, we get 0.23. And that's it. Questions for this one before we go to the next one? All right, the next example, rolling through. A sample of 147 students were asked if they lived on or off campus. The following contingency table gives a two-way classification, just like we talked about the car or truck one earlier. So we know that 29 males live on campus, 53 males live off campus, 52 females live on campus, and 13 females live off campus. Let's go ahead like we did earlier and find our totals. So how many males are there total? So 29 plus 53 will give us 82 males total. 52 females plus 13 more females would give us 65 females total. Just to check our work, that 82 plus 65 should give us a total 147, which it does. So we're good. Same thing for on campus. We have 29 plus 52. So total on campus should be 81. Off campus, 53 plus 13 more should give us 66. Total, just to check our work, 81 plus 66 should give us that total 147, which it does. So here's all of our totals. And it's just kind of personal preference. I just like to do that first always, so that way I'm done at everything that I need. So suppose one student is randomly selected from the group. Calculate the following, rounded 3 decimal places as needed. So probability of female. So we said total females was 65. Out of total was 147. So female out of our total. So 65 out of 147 would give us 0.44217, so 0.442. Next is female and off campus. Notice there's no given here, just female and off campus. How many females live off campus? 13. So 13 female off campus. Out of how many people total? That 147, just total. There's no given here, so it means out of our total. So 13 out of 147 would give us 0.0884, so 0.088. By the way, again, they want you to do it crazy. They want you to use the formulas and say, okay, it's going to be an and, so it's going to be one of these, or is it independent or dependent? I don't want to do all that. That's a lot of work. So just think about it like this. Female off campus out of our total. You get the same answer. And it takes 2 seconds versus this would take a long time. So probability of male and on campus. So how many males live on campus? 29. So 29 male on campus out of our 147 total. So 29 out of 147, which would give us 0.1972. So 0.197. All right, so probability of off-campus or male. So we kind of have to use the formula a little bit. So for off-campus or male, so how many off-campus totals are there? 66. Plus how many males are there total? 82. But in that 66 and 82, I counted that 53 twice because I counted it going down and I counted it going over. So we counted it twice. So I need to take it out one time. So minus off and male, which was 53, out of our total, which was 147. So up top, we have 66 plus 82 minus that 53, because we counted it twice. And that would give us 95 out of our total 147, which would give us 0.646. 0.646.
Why do you have to do the off and male?
Because I counted it twice. So whenever we said off, so we did 53 plus 13 to give us 66, right? And then whenever we said male, we said 29 plus 53. So I counted that 53 twice. So that means I counted that person, that male that lived off campus, I counted him twice, but I can only count each person once. So I had to take out the 53 because that was counted twice. Whenever it says or always means add. Whenever you add, you always have to think about subtracting. So notice whether it's independent, dependent, mutually exclusive, mutually non-exclusive, I always use the same formula for something like this, just to kind of keep it straightforward and easy. I'm all about easy. Same thing for the next one. It says or, so I know whenever it says or, I'm going to add. So probability of off-campus or female. So same thing. So off-campus, that total we said was 66 plus female. That total we said was 65. So in that off-campus and female, we counted that 13 twice. So the off-campus were counted in both groups, but it can only be counted as one person, so only once. So off and female, we're going to subtract, so minus 13 out of our total 147. So in my calculator, 66 plus 65 minus 13 would give us 118 out of our 147. Which would give us 0.8027, which will round up to 0.803. And that's it for this page. We have one more contingency table, and then we're kind of going to go a different direction. So before we go to that last contingency table, questions, comments, concerns for me, please. All right, I'm just going to say this. I don't talk politics, so I don't want to hear any comments. Sometimes I didn't say that last time, and I heard some comments. Agree or disagree? I don't know, not the place. So we're just going to do it, and it's just going to be numbers. It makes me very uncomfortable. So the random sample of 450 students and professors were asked about their political party affiliation. The following contingency table summarizes their responses. So 51 students were independent, 93 students were Republican, 88 students were Democrats. Same thing down here. This is professors. So 61 professors were independent, 99 professors were Republicans, 58 professors were Democrats. So same thing. It's the same contingency table, but now we have 3 options up top and 2 on the bottom. Same concept. Let's find out how many total students. So 51 plus 93 plus 88 will tell us how many students total, which is 232. On the bottom, how many professors were asked total? So 61 plus 99 plus 58, and that would give us 218. Just to confirm that we kind of hit everything, 232 plus 218 should give us that total 450, which it does. We know we did it right. All right, so then how many in each party? So independents, we have 51 plus 61, which is 112. Republicans, we have 93 plus 99, which is 192. And then Democrats, we have 88 plus 58, which would give us, thank you, 146. All right, so let's make sure that we have our total. So just adding up all of our totals. So 112 plus 192 plus 146 does give us that 450, so we know we did it right. So here's everything that we need. Same thing like we've been doing. So suppose one participant is randomly selected from the group. Calculate the following, rounded through decimal places as needed. So the probability that the person chosen is a student and independent. So we have 51 independent students. Out of our total 450. So in my calculator, 51 divided by 450, which would give us 0.113, rounding through decimal places. Probability of Republican and professor. So Republican professors, there's 99 of them. Out of our 450 total. So 99 out of our 450 would give us 0.22. Next is probability of Democrat or professor. So just like the or problems we did earlier, it's going to be adding. So we're first going to find the probability of, or how many Democrats are there. So out of Democrats total was 146. Just going to abbreviate it. Plus, how many professors are there total? Professors total was 218. Minus Democratic professors, which was 58. So Dem professors. Out of our total 450. I almost said 147 from the previous problem. 450. All right, so let's see. So up top, we have 146 plus 210 minus that 58 because we counted that 58 in the professor list and we counted in the Democrat list. So we counted it twice. So to take it out, and we're left with 306 divided by our 450, which would give us our total probability of 0.68. 0.68. Same thing for the next one, probability of Democrat or independent. So or means add, we're gonna do the same exact concept. So how many Democrats are there total? We said 146. Plus how many independents are there total? 112. Minus how many Democrat independents are there? 0. You can't be both. You're like in one party or another. So 0 out of our total 450. That would be our mutually exclusive. That's how you would use the other formula, but I don't even need to worry about which formula do I use because it kind of worked itself out in the wash. So cannot be both. All right, so 146 minus 146 plus 112 minus 0 would give us 258 out of our total 450. And we get 0.573. Similarly, last one, probability of being Republican and independent. 0. Mutually exclusive cannot happen at the same time, so they are none of those, so 0. So mutually exclusive cannot be in the Republican category and the independent category at the same time. Perfect. We're going to round out this chapter. A little bit different track. So before we go on that different track, questions, comments, concerns for me? All right, we're going to talk about tree and Venn diagrams next, just different ways of organizing and labeling our data. So a tree diagram is a diagram that helps us to visualize the different outcomes or the probabilities. For example, here is an example, a tree diagram that shows the probabilities when a coin is tossed. So the first coin is going to be if you land on heads or land on tails, 50-50. Here's our second coin. So if you landed on heads the first time, the second coin could be heads. The second coin could be tails. So this would be the option of landing on a head on the first time, heads on the second time, heads and then tails. Same thing down here. If you landed on tails the first time, your second coin could be a head or it could be a tail. So this would be tail head. This would be tail tail. Seeing all your different options just to kind of organize it. That's it. That's the tree diagram. Questions about that? Just seeing what it is and how it works. So next page is going to be a Venn diagram. We talked about Venn diagrams a little bit before with the and the or stuff. A Venn diagram helps us to visualize the relationships between different outcomes in a sample space. So this box represents all of the sample space. It represents our S. This circle represents what's in A. This circle represents what's in B. So this section is in A but not B. This middle section, what overlaps, what intersects, is in A and B. This section over here is what's just in B but not A. And don't forget about this part. This is the numbers that are outside. So it's not in A or in B. It's just outside in our sample space. So don't forget about that as an option. Questions about that before we do our last thing? We're almost done. Venn diagrams. So counting rule, factorial, combinations, and permutations. So for a counting rule, it means you're going to multiply together the total number of outcomes that can result from each step of the experiment. If an experiment consists of 3 steps, let's call those 3 steps M, N, and K respectively, then the total number of outcomes would be M times n times k. Let's do an example. Big Julius Pizza only sells pizza. They offer 3 different types of crust, 4 different types of cheese, 6 different types of meats, and 6 veggie toppings. If you order exactly 1 type of cheese, 1 meat, 1 vegetable on your pizza, how many different types of pizzas can you order at Big Julius? All right, so for crust, that's our first step. There was 3 options, it said, 3 types of crust. Times, using our counting rule. Our next thing says 1 type of cheese, so there's 4 different cheeses. That's our second step. 1 meat, they told us that there's 6 different meat options. So times 6. And lastly, 1 vegetable, they told us that there was 6 veggie options. So multiplying all that together, looking at our different options, 3 times 4 times 6 would give us how many different pizza options, and that would be 432 different pizzas you can order. So for this, kind of a little note, we're looking at the number of options for each step. Looking at the number of options for each step, and that's what gives us the counting rule. How many different options are there total? Remember that one, like I feel like this was always the question. If you have like 3 shirts, 2 pants, and 4 shoes, how many different like outfit combinations can you make? That's what would be our counting rule. Questions about counting rule? So next is factorial. Factorial, so it's not a really excited 0, that's factorial. So the number of ways possible to arrange n items, the product of all integers from n to 1. So if we're going to multiply all the different products from n to 1, but notice that 0 factorial is 1. And this is on our calculator, so we don't have to worry about actually doing a whole bunch of work here. So Wendy owns all 5 books of the Percy Jackson series. And how many different orders can she place all of them on the top of her bookshelf? So how many different orders? So how many different orders is telling me to use factorial? So there's 5 of them. So 5 factorial. So what that means is multiplying products from 5 down to 1. So 5 times 4 times 3 times 2 times 1. Which would give us 120. In our calculator, let me show you how to do it because it's a lot easier. So in our calculator, first type in the number. So first type in 5. Then we're going to hit our math button, which is right here, math. We're talking about probabilities, so use your arrows to scroll over to probability. Scrolling over to probability. If you notice, go down to number 4. Number 4 is our exclamation. Press enter. So that will give us 5 factorial, which equals 120. So one more time real quick. In my calculator, I press 5 first. Hit my math button, which is over here. Scrolled over to probability. Went down to our factorial. Press enter. Give me 5 factorial. Press enter. Done. All right, our last thing is permutations and combinations. Before I go there, questions on this one. So combination is the number of ways X element can be selected from n distinct elements where order does not matter. This is super important, where order does not matter. We have a formula for this. Notice for our combination, it's going to be C. So we have n, I call this as n choose C. So n is the number of sides in the set, and k is how many that's being selected. So this is always our total, like the number of sides in the set. So it's always going to be the bigger number. And this is how much you're selecting. So it's always going to be the smaller number. So the bigger is like the total. And then k is like the number being selected. We have a formula for this. This formula is on our formula sheet. N factorial all over n minus k factorial times k factorial. But your calculator has it, so it's a lot easier to just plug it into your calculator. It already has this formula programmed in it. Ready for the next page? Last page. All right, so there's 19 members on a city council. At a recent city council, 5 of the council members voted in favor of a budget increase. How many possible groups of council members could have votes in favor? So it doesn't matter the order, it's just saying how many of them are in favor. So no, order does not matter. So when the calculation involves permutations or combinations, it's going to be a combination because order does not matter. I don't care what order they said yes or no. I just want to see how many said yes. How many voted in favor? All right, so there's 19 members total. And we're choosing 5 of them. Or 5 of them are selected. So putting that, there's 19 total, and we're using combination, and we're choosing 5 of them. So it kind of helps me to say it that way. So there's 19, and we're choosing 5. 19, choosing 5. So you can put this into this crazy formula, but I feel like no one's going to do that. So let me just show you what you're really going to do. All right, so in our calculator, doesn't matter if you have an older calculator, newer calculator, we all have the same calculator. So in our calculator, let me break this on the side so that way you can follow along. First, type in 19. Then we're going to go to our combination. So going back to our math button, right here, math. So 19, then hit our math button. Again, we're going to scroll over to probability. Oops. And then notice number 3 is combination. So N, C, R, and then press enter. If you have a newer calculator, it kind of fills it in for you. But older calculator, it just has the big C, but it's the same thing. And then type in 5. So then type in 5 and then press enter. And that will give you your answer, 11,628. One more time if you missed it in the calculator. First type in your 19, then hit your math button. Right here's math. Scroll over to probability, go down to combination, which is number 3, press enter. You're choosing 5, so 19, choose 5, press enter. And there's our definitions. So there are 11,628 possible groups of 5 city council members who vote in favor of the budget increase. Who votes in favor? All right, so order doesn't matter. It's just how many vote, yes or no. Putting it together, it's combination. Questions on that one before we do the last one? Same exact concept for permutation. The only difference is now order does matter. So the number of ways X elements from N distinct elements where order matters. So where order matters. So here's our formula. Same concept. We have N, which is the size of this set, which is the bigger number, which is our total. Our permutation, so instead of our C for combination, we have our P, and then the number that's being selected, so that's going to be our smaller number. Number being selected. And if you want to do it by hand, you can use this crazy formula and go for it. But we paid a lot of money for these calculators, so we're going to use them. All right, so this example says a total of 19 horses compete in the horse race. How many different ways can the top 5 positions be arranged? So now if you want top 5, that means first place, second place, third place, fourth place, fifth place. Order matters. So order matters, you're going to use permutations. Permutations because order does matter. All right, so there's 19 horses total. Permutations because order does matter. And we're looking at the top 5. If you want to plug it into that crazy formula, you can. If not, we're going to do the same exact thing in our calculator. So in our calculator, we're going to type in 19, just like we did earlier. Oops. We're going to hit our math button. So third button down, hitting our math button. Again, we're going to scroll over to probability. We're going to go down to permutations. We're going to press enter to say that's what we want to choose. And we're choosing 5 of them. So type in 5 and then press enter, and that will give you your answer. So 1,395,360. So in the homework, don't put the commas. So 1,395,360. Possible ways in which the top 5 finishers can be arranged. So that's permutations, and guess what? That is all of chapter 3. Questions, comments, concerns on that? How could I help you? Remember again your formula sheet. This is the exact formula sheet that I will give you on test 2. It has all chapter formulas on it and chapter 4. So remember, before class next week, make sure to get your chapter 3 homework done. You have a whole week to do one assignment, just one chapter 3 homework. Next week we'll come in with chapter 4, so make sure to bring your chapter 4 notes. If you have any questions, I'm here to help you. Delaney is here to help you. Please let us know. If not, thank you so much. Have a great night. See you next week.